Hello and welcome to my video, lesson 3.4 on conductors in magnetic fields. So first of all, before you watch this, you have to understand the previous couple topics. So basically you need to understand about the three different types of hand rules. So those are very important before we get into this. But with all that said, let's take a look. When we have current flowing through a conductor in a magnetic field, the current feels a force. That's because when you flow current through a conductor, the conductor creates its own magnetic field. And when it creates this magnetic field, that field interacts with any other fields that are around. Okay, so it interacts with this field that it's in. So when you flow a current through a conductor, you can use your hand rule. So if you have a wire here and it's just a straight wire, then you can talk about your, you could use your first hand rule to talk about the magnetic forces around it. Or if you had a coil of wire, you could use your second hand rule to take a look at it. Or most of the time here, what we're going to do is we're going to be looking at the force that is occurring on the conductor. And so we use the third hand rule, just like in the last video with the charged particle. But now we're looking at a whole wire that has moving electrons, right? Along the wire. So here we have a motor, and we can tell it's a motor because it's got a battery here. So it's sending current through. Now, I don't remember if this is the right direction here, but if this is drawn properly, considering that the battery is looking like that, this would be the negative side and this would be the positive side. That's how AA's or AAA's look with the bigger knobby bit on the positive side. So we'll just look at it right now and see if this is actually indeed what's happening. So that means the electrons are flowing this way around the wire, okay? And so you can see that this is kind of cut off here. There's a little bit of a gap. It's a ring, but it's gapped. Okay, so that way there is no way it can hop early. It has to go along the wire path here. So as it goes along the wire path, it goes all the way around and then back through the battery. Okay, so let's look at this portion right here, which I'm going to show in green. So this part in green is what we're looking at. Now, if we look at that part, the electron flow is into the page. Okay, this is kind of a cross section of that wire. The electron flow is into the page. So you're going to point your thumb, just as this picture shows, you're going to point your thumb into the page. Now the magnetic field is going, as it shows in yellow, and I'm going to draw in orange, it's going sideways to the right. So your thumb is going into the page, the magnetic field is going sideways, which means that the force must be up. And indeed, that's what this is showing. And just a reminder, that's your left hand that you're showing that. So your thumb is into the page. Thumb. Okay, and then your fingers are showing the magnetic field. And the thumb was the electron flow. And then the palm of your hand is facing upwards. So that means, that's the force. And that's from the palm of your hand. Okay, and then if you follow the wire around, continuing the electron flow around over here, which I have in purple, not super clear where I'm drawing, but you can kind of hopefully see it's on the opposite side in purple. We have the same sort of thing, except that the flow is now coming out of the page. So everything else, the magnetic field lines stay the same, but now it's coming out of the page, which means if you point your thumb up, then your palm is down. So your thumb is up out of the page, your palm is down along the page, and the magnetic field lines are that way. So you can see how the force is being created on both sides, and especially since both of the forces are in the same sort of twisting direction, the entire thing will rotate, which is exactly what you want. You can just simply attach maybe a metal shaft on the other side. That's probably not a good color to work with. That's also not a great color to work with. Okay, I'm going to use this pink one, or fuchsia. So you can attach a shaft to this side over here, right there, or you could attach it to this part here and have it sticking out this way. So you have multiple options of how to, harness that motion. But once you attach the shaft, you can go ahead and attach it to a wheel or whatever else you want. Okay, so that's essentially how a motor works, an electric motor. Now, it comes from the interaction of the electron flow, which causes a magnetic field in the wire, and the magnetic field that already exists using some other permanent magnet usually, but it could even be another electromagnet. So it could be two different electromagnets in the same sort of system. Okay, to actually solve for the force, we have the following formula given to us. So magnetic force is I times L times B, where I is the current in the actual wire. The L is the length of the wire within the magnetic field, and then B is the magnetic field strength in Tesla. All right, so with that in mind, let's zoom out just a tiny bit. There you go. With that in mind, we have two different questions here. I recommend you pause the video now, try the questions yourself, and see if you get the same answer as I do. All right, so you're noticing a few things here. Your magnetic field lines are going this way. So I'm going to maybe draw 4 of them to represent that you're using all 4 fingers pointing in this direction. Okay, now the electron flow is going into the page. Okay, so the electron flow is going into the page, so that means that's your thumb. So this is your fingers. Okay, the blue here is your thumb. Okay, into page. Which means, last but not least, that means your palm is facing which direction? Well, down. So that must mean the magnetic force is down. Yeah, so that's just kind of qualitative, but we could look at a bunch of different examples like this. And I highly recommend that you do look at more examples from the textbook or something else. But let's take a look at another question. This one we may actually use that formula for it. So a 45 centimeter long copper wire has a mass of 55 grams and is carrying a current of 6.2 amps. At right angles to a uniform magnetic field, the apparatus is placed in a strong magnetic field and the wire is found to levitate. Calculate the magnetic field strength. So it is found to levitate. So that means, oh, and excuse me, this here is the magnetic field strength. That's B in the formula. Okay, and it's found to levitate, which means that if you look at the actual wire from the side, it's going to have 2 different forces on it. It's going to have force of gravity down, and it's going to have its magnetic force up. And it's levitating, so that must mean that your F net, I'm going to actually write it where we have a little bit more space. F net equals MA Well, the A is 0 because it's levitating, equals all your forces added. So Fg minus Fm. Now we can move the Fm over. Fg. Okay, so what we can do now is use the, formulas that we know. So Fg is mg. Fm is given at the top of the page here. So I, L, and B. And yes, I use L like this because I don't want to mix it up with either I or with the number 1. So I am purposely doing my L's a little bit funny. I never do L's like that. But when it comes to algebra, I always do my L's like that to try to avoid that error. So anyways, I'm solving for B. So it's going to go like this. mg over I, L. Okay, and then you can basically just simply solve it. So let's go ahead and try that out. All right, and if you plug all that stuff in, you get a result of 0.193387 Teslas, which we've got 2 sig digs, so 0.19 Teslas. All right. Yeah, I hope this video helps you better understand conductors and magnetic fields, and especially kind of the generator side of, the motor side of things. Generators are in the next video. I hope this video helps, and good luck.